Next probability function is probability density function or PDF. Probability density function for random variable capital X is denoted by a function that is small f, and it is a function of real value x. This probability density function can be expressed in terms of cumulative distribution function or CDF, denoted by capital F function small x. So PDF is expressed as derivative of cumulative distribution function with respect to small x, or small f function x equals to d upon dx of capital F function x. And here we note a point that both PDF and CDF are a function of real value x, but not function of random variable capital X. Now, as we know that CDF or cumulative distribution function can also be expressed in terms of probability mass function with an event capital X less than or equals to small x. So PDF can also be expressed as d upon dx of probability of occurrence of event x less than or equals to small x. And it is very important function in communication system for mathematical analysis. Next, we talk about the properties of probability density function or PDF. The first property of function PDF is always a non-negative function, that is for all real value x. So, small f function small x is always greater or equals to 0. Next property is, here the cumulative distribution function denoted by capital F can easily be recovered from probability density function or PDF. Using formula, capital F function small x equals to integration of small f function s into ds. Here small s is taken as a real value for our convenience, and limits of s is from minus infinity to small x. And the last third property is, when we take a limit real value x tends to infinity in integration, then the value of integration is always equals to unity, which represents the total area under the curve is unity. Also, as we know, when we put limit x tends to infinity, then the value of CDF equals to 1, but when we put x equals to minus infinity, then the cumulative distribution function becomes 0. So accordingly, the value of integration is unity, that is unit area. Now let us take an example of PDF, that is probability density function, with the random variable x as uniformly distributed, which means it totally fulfills all the properties of probability density function. That is, the first property is it must be a non-negative function, and the second is area under the curve must be unity. And this type of probability density function is called uniformly distributed PDF, as shown in figure. Here the real value small a and b are positive and area under the curve is unity. So mathematically, small f function x equals to 1 upon b minus a for x greater or equals to a, less than or equals to b, and 0 otherwise. Next, we discuss the joint function corresponding to CDF and PDF. So, CDF with joint probability is called joint distribution function, and PDF with joint probability is called joint probability density function. To explain these joint functions, we consider two random variables x and y. These random variables x and y expressed two different experiments, or it may be a single experiment repeated twice. So accordingly, the joint distribution function is related to CDF function of individual random variable x and y, and it is expressed as capital F function x comma y equals to probability of occurrence of event x less than or equals to small x comma y less than or equals to small y. And here the limits for random variable x is greater than minus infinity but less than or equals to small x. Also, capital Y is greater or equals to minus infinity but less than or equals to small y. Similarly, we can express the joint probability density function using relationship with joint distribution function, and it is expressed as small f function x comma y equals to del square upon del x del y of capital F function x comma y. Here suffix capital X comma y represent two random variables corresponding to two different or repeated experiments. Now next we discuss the properties of joint CDF and joint PDF. So first, as we know that the CDF is bounded between two values 0 and 1. Similarly, the joint distribution function is also bounded between 0 and 1. So capital F function x comma y is greater or equals to 0 but less than or equals to 1. Also, when we put x and y, that is a real value, tends to minus infinity, then the value of joint distribution function is equals to 0. But for plus infinity, its value is unity, which is same as the case of cumulative distribution function. Now next property is, as the CDF is a monotonic non-decreasing function of single random variable x, so the joint distribution function is also a monotonic non-decreasing function. Which means if x2 is greater than x1 and y2 is greater than y1, then the capital F function x1 comma y1 is less than or equals to capital F function x2 comma y2. Which means the joint distribution function is always a monotonic non-decreasing function for both real value x and y. Next, we discuss the properties of joint probability density function, or simply called joint PDF. Joint PDF is expressed in terms of joint distribution function, and it is denoted by small f function x comma y equals to del square upon del x del y of capital F function x comma y. So the first property of joint PDF is a non-negative function for all values of real value x and y, and it behaves as a monotonic non-decreasing function. So small f function x comma y is always greater or equals to 0. Second property is the total area under the curve of joint PDF is always unity, which means in integration, as real value x and y tends to infinity, the result becomes unity, or total area becomes unity, which is same expressed in case of probability density function properties. Now we extend our discussion with joint PDF to marginal density function. To explain the concept of marginal density function, we consider a joint distribution function denoted by capital F function x comma y, that is equals to probability of occurrence of events x less than equals to small x comma y less than equals to small y. This joint distribution function can also be recovered from joint PDF using double integration. Now for our convenience, we take psi corresponding to real number x and eta corresponding to real value y. So the joint distribution function, that is capital F function x comma y equals to double integration of small f function psi comma eta d psi d eta, with limit psi equals to minus infinity to x and eta equals to minus infinity to y. So this is a simple representation of joint distribution function in terms of joint PDF. Now, to obtain a marginal density function, we simply take a finite range of one random variable. It may be x or y, and put infinite limit to other variable. For example, first we take a finite limit of variable x, that is psi equals to minus infinity to x, and put other limit y tends to infinity. So in this case, the function becomes marginal and written as capital F function x comma infinite, and this is called marginal density function. Also, we can put x tends to infinity and take a finite limit of y, that is eta equals to minus infinity to small y, and in this case marginal density function is capital F function infinite comma y. So the marginal density function is simply defined as the PDF of single random variable that can be obtained from joint PDF by taking entire range of other random variable. Now for our convenience we can write capital F function x comma infinite as simply f function x. Also f function infinite comma y as capital F function y. Now in the case of f function x we differentiate both sides with respect to small x. So it becomes d upon dx of f function x and the integration with respect to x cancels out and we get an infinite range of variable y. Here as psi correspond to real value x, so in place of psi we can write x and this is called PDF, that is small f function x. Similarly for capital F function y we differentiate both sides with respect to y and here the finite limit corresponding to variable y cancels out and put eta equals to y, we get PDF, that is small f function y. As these PDF are obtained using joint PDF taking infinite range of one of the random variable, hence called marginal density function or marginal PDF. After discussing marginal PDF, we move to conditional probability density function. To understand conditional PDF, we consider two random variables x and y that depend on one another. Then it can be easily observed that knowing the value of one of the random variable, other random variable would be expected, that is on the basis of some conditions and statics. Now let random variable x is given and assigned by a real value, that is small x. Then conditional PDF of random variable y is given as a function, that is small f function y provided x is given and it is equals to the ratio of joint PDF upon marginal density function of given random variable. So conditional PDF correspond to random variable y is a ratio of f function x comma y upon f function x. Here f function x, that is marginal density function of random variable x, is a non-negative value. Next we discuss the properties of conditional PDF. First property is the conditional PDF, that is f function y provided x is given, is always greater or equals to 0, which means it is a non-negative function. Second property is the area under the curve of conditional PDF is equal to unity. So the integration of f function y provided x given into dy is equal to 1. Now we note a point. If random variable x and y are statistical independent, that is not depend on each other, then the conditional PDF of random variable y is equal to the marginal density function of random variable y, which means f function y as x given is simply equal to f function y, and this can be understood using the formula, that is f function y for x given equals to ratio of joint PDF upon marginal density function of x. Here we consider x and y as statistical independent, then the joint PDF function f function x comma y is simply written as the product of their individual marginal densities, that is f function x and f function y. So after putting marginal density function corresponding to random variable x is cancelled and we get only f function y. So for statistical independent random variables x and y, the marginal density function is same as conditional probability density function.